In Unit 8, we're going to look at rational expressions and equations. And if you remember, rational expressions and equations are fractions. So when we see rational, really what that means is it's a fraction. So we're going to look at simplifying rational expressions, multiplying, dividing, adding and subtracting. We're going to look at some more simplifying with what we call complex fractions, solving rational equations, and then we're going to look at some application problems. So in the first lesson, we're going to focus on how to simplify rational expressions. So remember, rational expressions just means fractions, and they're actually going to be a polynomial over another polynomial. So this first definition here is just saying a rational number. It's a number that's expressed as a fraction, and the denominator cannot equal 0. If you remember, whenever you have 0 in the denominator, that expression would be undefined. So when we're talking about the definition of a rational number, it can't have 0 in the denominator. The definition then of a rational expression is when we have a fraction that has two polynomials and the denominator, again, cannot equal 0. If it does equal 0, we have to say it's undefined. So here's just some examples of rational expressions. So you have a linear term over a linear term, quadratic over a quadratic, another linear over a linear. So this first property here is that if you were to multiply by k, you would do it to the top and bottom, and you would get an equivalent expression, p times k over q times k, where p, q, and k are all polynomials. And the same works for dividing. You can divide the top and bottom both by k, and it would still be equivalent. So that's going to be useful when we look at simplifying. It'll also be useful when we come back and we do simplifying complex fractions. So for these first examples, all we're going to be doing is reducing these rational expressions. So when you reduce, what you always want to do is simplify each piece first. So you're going to simplify first. And then what you're going to do is you're going to look for common factors that will cancel out so that you get your fraction in lowest terms. So you always want to check the top polynomial and see if you can factor it. So factoring is going to come back into play here. So I have x squared minus 9, which is a difference of perfect squares. So you can factor this as x plus 3 and x minus 3. You take the square root of both pieces and you do opposite signs. And then the bottom, I can't reduce that, so I'm just going to leave it as x minus 3. And then since the top is now a product between two factors, I'm allowed to cancel by division because dividing undoes multiplication. So x minus 3 is the same, so it's just going to become 1. And I'll be left with x plus 3. So that would be this fraction reduced into lowest terms. So same process for the next example. We look at, can we factor the top? And the top is going to actually be quadratic factoring. So you're looking for what adds to negative 5 and multiplies to negative 6. So you're going to have two sets of parentheses. You're going to use y and y, split that up. You're going to have opposite signs if you're multiplying to a negative, so plus, minus. And if you're multiplying to 6, but you're trying to add to negative 5, that means the bigger number has to be negative and the smaller number is going to be positive. And in order to multiply to 6, it's going to be 6 and 1, so that when you add those, you get negative 5. And then down at the bottom, you look to see if you can factor, and you can because it's a difference of two perfect squares. So you're going to have two sets of parentheses, opposite signs, and you're going to square root each piece. So the square root of y squared is y, square root of 1, we get 1. So then you look for, now that it's multiplication, you look for pieces that will cancel, which would be those. So we're left with y minus 6 over y minus 1. So let's look at some more examples. So again, factoring. I always check for GCF factoring. So I look to see if I can take out a GCF. Always do that. So in this top piece, I can take out a GCF of 2. And I'll be left with a to the third minus 8. And then on the bottom, it looks like I can take out a 4. I usually check those coefficients in front of the highest variable, or the highest degree. So when I do that, I could take out a 4, and I'd be left with a squared minus 3a plus 2. And then you want to see, can you factor this further? So the top, I can actually factor that a to the third minus 8. That's a difference of perfect cubes. So when you do that kind of factoring, remember you take the cube root of each piece. So cube root of a to the third is a. Cube root of 8 is going to be 2, and then you keep the sign between it, that minus 2. And then the next piece of the formula says you take this a minus 2, you square the first term, switch the sign, multiply the two terms, so 2a, and then add the last term squared. So 2 squared gives me 4. And then at the bottom, I have 4, and then I want to see if I can break this up into quadratic factoring. So add to negative 3, multiply to 2, which tells me that I'm going to have the same sign, and they're going to both have to be negative since I'm adding to a negative. And my answers are going to be 2 and 1. And then we want to see if we can go any further. So right now I see that these are going to cancel. I'm also going to be able to reduce this 2 into 4. 2 goes into 4 2 times, so there'll be a 2 left here, and I'll just have a 1 up top. And then I want to check this piece here and see if I can factor it. So I want to ask myself, is there anything that I can add to 2 and multiply to 4? So there's no numbers that are going to work because the only way that you can get 4 is by 4 times 1 and 2 times 2, and there's no way to combine those and get 2. So you're just going to have to leave that as is. So that means our final answer is going to be a squared plus 2a plus 4 all over 2 times a minus 1. And if you wanted to, you could distribute that too, you just don't have to. So more examples with reducing. So we have this first piece, now we have 4 terms, which is a good indication that I'm going to have to do factor by grouping. So all of these factoring techniques are really coming back here. So since you have 4 terms, I'm going to split it, and I'm going to see if I can take a GCF out of each individual piece. So the GCF of the first is going to be x, so I'll be left with an x minus 3. And then for the second one, I can take out an a, so a positive a. So I'd be left with x minus 3. And then on the bottom, I'm going to do the same thing. So I can take out an x out of the first term, so x minus a. And then it looks like I can take out a negative 3, because remember, I'm trying to get x minus a. So since I have a plus there, I really want to take out, I want to switch the sign, so I'm going to take out a negative 3. So I'm going to take out a negative 3. I'll be left with x minus a. And now you're going to take out each of these pieces. So now I can take out the x minus 3, and I'm left with x plus a. And then here I'm going to take out an x minus a, and I'm going to be left with an x minus 3. So then the pieces that cancel, I'm going to have x minus 3 that's going to cancel, and I'll be left with an x plus a on top over an x minus a on the bottom. For example 5, I again want to reduce this. Now you might be thinking, well, there's not anything that I can factor. If you look at the top, I can't factor. If you look at the bottom, I can't factor. So whenever you have a scenario like this, you want to remember the pattern that since these two are basically the same thing, but the difference is the a and the b are switched, and subtraction's not commutative, you can't just cancel them. But what you can do is you can think of it like this. So if I have b minus a, that's really the same thing as negative 1 times a minus b. Because if you were to distribute this negative 1, you would have negative a plus b. And then since this is addition, you can switch the order, which is b minus a, or b plus negative a, which is b minus a. So these two things are equal. So if you just remember this rule, that whenever you have an a minus b or b minus a, you can just basically replace it with negative 1 times the opposite. So that's how we kind of compensate for the fact that subtraction is not commutative. So what I can do is I can keep the a minus b on top, and on the bottom I can rewrite that as -1 times a minus b, since this is equivalent to b minus a. And then what that allows you to do is it allows you to cancel those. So you'll have a 1 on top and a -1 on the bottom, which just means that your answer is -1. So similarly, down with this example, we're going to reduce. So we're going to look at the top. We get x minus 5 times x plus 5 when we factor, because it's a difference of perfect squares. And then on the bottom, I have a 5 minus x. Now, I can't cancel anything as is, but what I can do is, since these two are the same but opposite, what you can do is you can cancel those, but you just have to remember to replace it by a -1, because essentially what I'm doing is I'm replacing one of them. So let's say I'm replacing x minus 5 as -1 times 5 minus x. So I just replaced, so really what I did was I took this and I replaced it with 5 minus x times -1, and then I canceled the 5 minus x's. You just don't have to show it. You can just basically cancel it and put a -1. It doesn't matter where the -1 goes, on top or on bottom, it'll always work. So your final answer will just be negative times x plus 5, which if you distribute it, you'd get -x minus 5. So either one of those is acceptable. And then one last thing for this lesson. So the last thing here is really just focusing on the definition of a rational equation or rational expression, and it's finding when the equation or expression is undefined. So in this case we have equations, but it would be the same thing if you had expressions, meaning no equal sign. You want to find the value for x when the equation is undefined. So when this equation is undefined is when there's a 0 in the denominator. So basically what you do is you're just going to set the denominator equal to 0. So I had x minus 2 equals 0. Solve that, so bring over the 2, you get x equals 2. So the equation is undefined when x equals 2. So undefined when x equals 2. That's what it means. So for the next one, if you want to figure out when this is undefined, it's when the denominator equals 0. So you're just going to set the denominator equal to 0, solve it, so we get x equals -1. So that means the equation is undefined when x equals -1. So that's it for this lesson. In the next lesson, we'll start looking at operations with these rational expressions.